Well, on behalf of the organizing committee, I welcome everybody here to the new series of seminars of the IAU Commission J1. As you know, we plan to have presentations on topics related to the remit of this commission, which is the spectral energy distribution of galaxies, and the talks will take place every other month on the second Monday. And we also note that the talks will be uploaded to the IAU YouTube channel. We will advertise this properly as well. So today we are very happy to thank Aaron Robotham for giving us the first talk of this series. Professor Robotham is based at the University of Western Australia, and he's principal fellow at ICRAR, the International Centre for Radio Astronomy Research, a joint venture between UWA and Curtin University in Perth in Australia. So Aaron is an expert on extragalactic astrophysics and has very actively contributed to several large galaxy surveys, most notably, of course, GAMA, also SAMI, many others, and now as well Foremost Waves, where he's a member of the project office. His research also includes a wider range of applications of various statistical techniques to the analysis of astrophysical data, and he has produced a good number of computer codes to analyze images and spectra. And today he will tell us about how to incorporate evolving metallicity, AGN, and radio emission into SED fitting. So thanks, Aaron.
Thank you very much. I will share my screen now. So, and I'll start my talk on my side.
Good.
I'll just move that over there, and hopefully that is appearing for everyone.
Yes.
Thumbs up.
That's good. Yep.
Good. Well, thank you very much for having me. It's a pleasure to be here virtually, particularly to present this work on Prospect, because the paper happened, as you'll see a bit later, pretty much at the beginning of COVID, so it somewhat prevented us going around in person and giving talks on it. So it's always nice to present it. So I'm Aaron Robotham, as I was nicely introduced, but I particularly want to emphasize a lot of the work I'm presenting is stuff that was done by my recently completed PhD student, Jessica Thorne. You'll see her name at the bottom. And current postdoc working with me, Sabina Belstedt, who I think is even online. So a lot of the work is theirs, and I'll try and highlight where appropriate, but also completed PhD student Matthias Bravo and a colleague of mine at ICRAR, Claudia Lagos, who I'm sure some of you know on the simulation side. So again, thank you very much for the invite. And I'll kick off. So I'm going to briefly talk about the galaxy redshift surveys I'll be using for this talk. Won't dwell on that too long because it's probably not super interesting to most of the audience here. Get a bit into the background of the basics of SED fitting, just to show how we're going to kind of build on that to do novel things. I think novel things, you'll agree. How we do this in Prospect in particular, and then more of a focus on this recent work, particularly done by Jess. So I did a lot of the software, Jess did a lot of the analysis in the paper, but on AGN fitting and the radio extension. So I think that's where it gets particularly interesting for most of this commission, and then obviously a summary. So briefly on the redshift surveys, one of the two was already mentioned in that introduction is GAMA. I'm sure most of you are aware of this. It was one of the larger even focused redshift surveys that operated on the AAT, finished quite a few years ago, but what really made it novel and useful and relevant for this commission and SED fitting in general is how multi-wavelength it is. So the focus observation on our side was getting the spectra from the AAT, about 300,000 redshifts, but also really getting that UV through to certainly far infrared, but now finally getting ASCAP and even GMRT data. So really the full domain of where galaxies pretty much emit their light, everything except, you'll notice, really X-ray. But actually this slide's slightly out of date because eROSITA did actually target the gamma fields. So we are now finally doing work incorporating even the X-ray data. The other main survey we talk about is DEVILS. Think of this as the higher redshift kind of analog to gamma. So you see gamma there at a medium redshift of about 0.25. DEVILS was also conducted on the AAT, but had quite a different wide magnitude down to 20, fewer galaxies, because it's harder to observe these things, about 20,000, and smaller fields. So you see at the bottom, the gamma fields are the things in kind of orange. In the background for reference, you've got the Milky Way plane in brown, the ecliptic plane in kind of that light kind of orange color, and the three small DEVILS fields, which make up about 3 square degrees in this kind of greeny teal color. So really, all the work I'm presenting here was done at very low redshift with gamma, largely by Sabina, or at high redshift with DEVILS largely by Jess. Okay, so that's the kind of the data that goes in. I'll try to highlight that when it happens, but please ask if you're curious. And just a bit of a reminder, I'm sure everyone's familiar, but no one minds hearing some of the basics again, just to know where we're starting from, a bit about SED fitting, kind of 101. So this is a nice graphic by a colleague here, Luke Davis, showing kind of almost all the emission you might expect from kind of a real plausible galaxy, going from hard X-rays on the left-hand side all the way through to kind of even self-absorbed kind of synchrotron emission on the right-hand side, kind of surveys like GLEAM and GLASS, and obviously now EMU. Kind of in the middle is where I've probably spent most of my career. You can see these two classic bumps. So you've got your kind of UV optical near-infrared output, your little mid-infrared wiggles in the middle from your PAHs, and then your dust on the right. So you can see actually below the SED, this kind of toy SED, we've got kind of which physical processes are more or less ignoring AGN, largely in the optical near-infrared regime, I should add here. But you can kind of see what processes are kind of dominating, kind of roughly where young stars tend to dominate the spectra, the old stars, the various hot dust mechanisms, and then on the right, your free and synchrotron. So that's sort of your kind of classic thing, but obviously we want to take observations of spectra, usually broadband photometry, given the kind of surveys I work on, and try and infer these physical properties and, you know, say something meaningful about the universe. So we kind of zoom in and see what we're generally doing. A very simple kind of recipe might be you take your pure star template. We'll kind of get to some examples of that and which ones we use in prospects soon. Some sort of attenuation, again, a few options about how you do this. But basically, you've got some mixture of dust and probably birth cloud attenuation that reduces kind of the emission of your stars. And obviously, that gets more dramatic the bluer you go. And some sort of recipe to re-emit that absorbed kind of dust in the far infrared. So that's where your kind of PAHs and your kind of far infrared bump come into play. Put that all together and you get something that looks like a classic SED. So that's the very quick basics, which I'm sure everyone's familiar with, but what we do in Prospect is kind of where I think things get more interesting from your point of view. So what do we try and do in Prospect? Well, just as a advert, if people want to note down, these are the core, I guess, Prospect papers. All came out in about 2020. My original one literally has Prospect in the title. I assume Matthias Bravo did action to simulations using kind of the generative mode of Prospect. Then Sabina's work, which we'll get to, looking at the cosmic star formation history. Claudia's work, plugging Prospect into Sharp, semi-analytic galaxy model, and then Jess's kind of first paper for my PhD, looking at like stellar masses and star formation rates, and kind of the low-hanging fruit from DEVILS. So our basic kind of pseudo galaxy model, I say pseudo because there's nothing intrinsically 3D going on in Prospect, but you kind of have to imagine in your head when you're writing the code that there's sort of a real galaxy you're trying to simulate. In the case of Prospect, we have star formation kind of in something like ISM kind of large cloud, which clearly gets attenuated. You'll see, depending on your point of view to this toy galaxy, if you happen to be observing this galaxy kind of all the way through kind of the edge-on disk, so visually it would look like kind of an edge-on in a spiral. Clearly light's going to get more attenuated and become kind of redder and redder and redder. That's pretty simple. Clearly, if you saw this face on, which is that view from the bottom, that kind of effect is less extreme. So in both cases here, the kind of blue dashed unattenuated stars, see the plots on the bottom, that's exactly the same spectrum. All that's changing between kind of the left-hand plot and the right-hand plot is how dramatic your attenuation is. So clearly you're more attenuated, and your kind of observed SED gets visually redder on the right-hand side. We are kind of looking through all of the ISM dust in particular. So that's kind of the toy model that's going on inside Prospect. You'll notice I do mention an active galactic nuclei here. This was the basic early implementation for my 2020 paper. That changed quite a lot by the time we got to the stuff I'll present that Jess did much more recently. But again, we have a basic kind of semi 3D, like a 3D motivated model of an active galactic nuclei, which does have something like effectively a dusty torus kind of orientation available to it. So when we do SED fitting, there's a number of things we have to worry about. These are like the big ones. You have to worry a bit about star formation histories. So the rate that you form stars with time, that's pretty basic, but there's two main kind of approaches which are popular these days. Non-parametric, which is actually a lie. It is parametric. It's just stepwise parametric, but astronomers tend to like that branding. I don't actually quite appreciate why. And full parametric, which is like smooth functional. You have obviously stellar templates or stellar population libraries, SSPs, they're called a variety of things, but you'll recognize the classic ones like BCO3, FSPS, emailers, and even Mariston 05 is an example there. Different recipes to attenuate the dust. Probably the most are Charlot and Full and Calzetti. I'm sure those are familiar to you. You have a recipe for how you remit your dust. So Drain and Lee, probably about the most popular, or Grey Body and Dale, which is actually the one we use, which you'll see. You have to worry about your initial mass function. Chabrier and Krupa are probably the two most popular these days, particularly Chabrier. You might, not all codes do this, have to worry about how you want to emit lines. So your emission lines, your two main approaches are using recipes from the famous codes Cloudy, or being based in Australia, I've gravitated towards Mappings 3. You'll have to worry in some sense about the metallicity. The two main approaches are other, which we'll get to, and constant but free. Really, other is often completely fixed. And this middle one, which is kind of a focus for the early part of this talk, is this mechanism to have evolving metallicity. Other things you might want to be able to do would be an extension into the X-ray, spectral line fitting. Most kind of SED codes don't do that, and a radio extension, which is the last part of this talk. And you might want to worry about AGN templates. So again, there's kind of classic ways to do this, Dale, Casey, and in our case, Fritz model. So I'm going to show what Prospect does first before we see some kind of competitor, but let's say complementary. I don't always see it as competition exactly. This is the recipe that Prospect has. So the focus here, if you look kind of where the redder boxes are, that's kind of how popular these implementations are. Prospect does do parametric and non-parametric. It actually now, as you'll see towards the end, has access to both emailers and BCO3, but also now BPAS. Charlot and Full dust model, Dale dust emission, all Grey Body, but in practice we always just use the Dale mechanism. Chabrier IMF, Mappings 3 emission lines, evolving. Nearly always we use the evolving metallicity mode, as we'll get to. Now it has a radio extension, thanks to Jess's work. And on the AGN side, we basically use this Fritz kind of more sophisticated 3D model. So you also have to worry about, when I mention the stellar population codes, they themselves, I won't go spend nearly as long on this slide, but BCO3, Mariston, BPAS have added here, FSPS and emailers, all make their own decisions, particularly about which family of isochrones they use. There's a lot of options here. Nearly all of them do make use of padover, but you'll notice that there are some exceptions. BPAS does its own thing. It uses the Cambridge stars isochrones, which is what allows it to really deal with binary populations in the fairly unique way it does. They also have to make kind of some decision about what like stellar atmospheres they'll use and how they combine them, and also the IMF. I think pretty much all of them, I've got one arrow missing, which is Mariston, make use of Chabrier, or very similar in practice. But these are the three big choices. So even those stellar population libraries can have quite distinct differences inside of them. So if I add on the other kind of classic codes, ones you'll definitely be familiar with, things like Magfizz and Segal, also perhaps more recently and unfortunately similarly named Prospect Or. These literally happened about the same time. I guess my kind of software I develop always starts with a pro, so I was kind of committed, and then it was too late by the time I discovered there was a Prospect Or being developed at the same time with no capital S. So they're slightly differentiable but annoyingly similar. But more recently, stuff like Beagle and Bagpipes too. I know this is a chaotic diagram, and it's kind of meant to be, just put this together for a first paper. It just shows when you really dig down how many different reasonable but impactful decisions kind of are going on when people assemble these codes. So even making different choices in the stellar population libraries, even if everything else is similar, can have a pretty big impact. The strength of those black boxes is really representing how popular really those are. So nearly everything has access to BCO3, nearly everything has access to Charlotte-04, nearly everything uses Chevrolet, most things use Cloudy, most things when it comes to Metallicity are constant but free, which we'll get to, and most things are parametric star formation histories. Okay, and the only addition here, if I go back, is I've added BPAS. So since Jess did her first paper, we added the BPAS stellar population library. In practice, all the stuff I'm presenting here uses BC03, but feel free to ask me a bit about the impact of layers and BPAS and some of this work, because we have looked into that. So the first thing I'm going to talk about a bit is star formation histories and metallicity kind of evolution. Kind of a classic way of looking at star formation history would be, is it parametric, which means it's a kind of a smooth sort of functional form, or again, I'll say in speech marks, non-parametric. It's still parametric, but tends to be stepwise, or at least there's discontinuities. So the classic thing on the right-hand side would be a bunch of step functions that represent the rate you form stars for time. And on the left-hand side, probably about the most popular exponentially declining star formation histories, sometimes with a burst at the end, which prospectors have the option for. What we do is a bit different. After a lot of experimentation and feedback, particularly this part of the work I did working closely with Sabina, because it was very, had a huge impact on cosmic star formation history reconstruction, is the right form to use to define star formation history. So we ended up using a sort of skewed normal. So if you look at the kind of light yellow line, that's almost perfectly normal or Gaussian, but you can see on the far right hand side where you've got that orange function is quite skewed, to the right, and on the left hand side you can see that teal kind of lower normalization star formation history, which is skewed to the left. Now the key thing is what we do in metallicity, we've got the option to actually couple it to the rate at which we form stars. So a bit where those yellow lines to the left appear, they actually are coupled directly to how we build up your metals. So if you look, for instance, that kind of orange star formation history, which peaks at about 13 gigayears in this case, you can see that builds up its metals almost straight away, and then it plateaus and saturates because we're linearly mapping the metallicity growth to the mass growth. I'll get to why that appears to be reasonable and more physical than other kind of routes, but it turned out to be really important to actually get the right kind of shape and normalization of the cosmic star formation history, which was one of our targets, to check that Prospect was doing something kind of physical rather than arbitrary. Okay, so we have a few parameters we can control with the star formation history. This MSFR, that's basically a normalization term, controls the maximum star formation rate. MPeak controls the location of where that peak is. M period is basically the width of that star formation period. Then skew is how far skewed to the right or left it is. And in terms of the linear mapping, the main free parameter we ended up using was just Z final. So in fact, we always fixed the origin method to be the lowest value of successful in BCO3. So what's the impact of all of this? Well, if you compare to MagFizz, which we had, the main reason we compared to MagFizz here is we did all the analysis on gamma already using Elisabetta Dacuna's MagFizz code. She also kind of works at ICRAR, just down the corridor from me. So we had those comparisons to make of stellar masses and star formation rates. So obviously it was natural we wanted to see how Prospect compared. MagFizz uses exponentially declining plus birth star formation histories, or at least it did back when we did that work. And in terms of metallicity, it's constant but free. So it can basically move up and down, but it is always the same metallicity when you're forming stars, whether it's right at the beginning of when you start star formation or right at the end. The impact of kind of our decisions on how we want to do SED modeling is Prospect systematically recovers more stellar mass than MagFizz. This is for the same IMF. The other fundamental things are very similar. By about 0.15 to 0.2 dex. And obviously, not obviously, but also slightly higher normalization in the star formation rate. But the main impact is an increase in stellar mass by a fairly appreciable amount. That's often above kind of the quoted, let's say, error, systematic error in stellar mass, which is usually around the kind of 0.1 to 0.2 dex mark. Do we think metallicity matters? Well, If you look at your kind of SED, kind of we zoomed in a bit earlier, kind of take that apart, and we look at, let's make a 10 to the 10 stellar mass galaxy with a constant star formation history. So in this case, I think we literally formed one solar mass a year for 10 to the 10 years, so 10 gig years. If we do that with the constant solar metallicity and everything else kind of set to the same settings, we can compare to what happens if we start to have different metallicity implementations. So here is the impact of that. Everything the same, just varying metallicity. If we switch to a quarter solar metallicity, hopefully it's no surprise, but the effect of a quarter solar, so lower metallicity, is a bluer spectrum, kind of a flatter spectrum in the optical near-infrared regime. So you can see that's the purple. If we go to ×2 solar, it gets redder. Again, this is your age, metallicity, sort of degeneracy stuff starting to appear. But interestingly, or the reason it's constrainable is if you go to this closed box, which is very similar to linearly mapped, I should add, a closed box evolution with solar metallicity as the final kind of destination, rather than being systematically blue or systematically red, ends up kind of pinched in the UV and pinched in the near infrared, but bulging out kind of in the optical. So basically, if you have high enough signal to noise data, and we have very good photometry of gamma and for DEVILS, then if closed box evolution is the right answer, it ought to be measurable. So then what's the impact of that? So we actually redid the sample of low redshift galaxies. There's about 6,000 galaxies in gamma below a redshift of 0.06. And this is really Sabina's work in 2020. You can actually look at different ways of fitting these galaxies, stacking their star formation histories, doing a volume correction, of course, and seeing what implied cosmic star formation history you get. If you take all those star formation histories and stack them back over time, hopefully it's consistent with, for instance, McDowell and Dickinson. If it's heavily not, then something's, internally inconsistent. So if you do a crazy thing and say it's fixed, but like the floor, almost the floor, not quite, of BCO3, then you get a very unphysical stack. You get all your stars forming in the early universe. The integral is not completely off, but it clearly doesn't look anything like the real universe. Our next kind of simple model, if you go to a bit subsolar, but not crazily, so 0.01, again, it's just constant. It's not allowed to evolve. It's still kind of biased to forming stars too early. If you actually plugged it to solar, then you suddenly flip and you get kind of the opposite extreme, which a lot of similar work has found. You tend to get this bulge at kind of middling cosmic look back time. So you basically don't get the peak where we know cosmic noon roughly exists. It kind of peaks much more recently. If you have it free but constant, so a bit between the two, it's starting to look a bit more healthy. So it doesn't peak quite as early and it sort of plateaus. So this is more, say, in the spirit of how, I guess, magphys would operate, but with a different star formation history function, not just fixed, be exponentially declining. If you literally made it linear, and I don't mean linearly mapped, I mean literally linear, then it kind of almost looks worse. You end up with this ugly bulge in the middle. This was one of the recipes we looked at before. We had the realization that something like closed box devolution was much more physically motivated, and it was probably worth investigating what impact that had on cosmic star formation history. So that's all of them put together. Like I said, the better answer turned out to be, and ended up being similar, but here I've shown Sabina's line for closed box. So where every single galaxy grows its metals in a closed box way. In practice, the next slide I'll show you, we actually ended up switching to linear, and you'll see why soon. They're very similar. They have slight differences, so there's not a huge game-changing difference whether you use closed box or you use linearly mapped, but it's getting much nearer to what we think the cosmic star formation history should look like. This is a plot from Sabina's paper, which uses, I think, now the linearly mapped variant, but again, visually it's very similar. On the left-hand side, we're seeing the build-up of, the cosmic star formation history on the top. We do form more stars in the earlier phase of the universe than, say, McDowell and Dickinson, but it's not completely incompatible now. The bottom is just a build up of the stellar mass and density. And the right-hand side is just a breakdown of different visual morphological types. So we look at redshift 0 elliptical galaxies, Not surprising, probably. We can see they form most of their stars when you trace them back forensically in the very early universe. But if you look at disk galaxies, particularly SED, kind of irregular kind of classes at low redshift, they have actually something that looks pretty close to a kind of constant star formation history over cosmic time. So what really motivated that kind of functional form was work I did with Claudia, which was taking SHARC, a semi-analytic galaxy model, which I collaborated on, applying a forward modeled version of Prospect to generate SEDs, and then actually trying to do the inversion and see which best recovered the actual growth in stars and metals that, at least in SAM, we knew was what was happening. Okay, so that was like our control. So all those black lines are actually what's really going on inside SHARC, and we're showing kind of consistently a red line, which is Prospect using an S-norm function with this evolving linearly mapped metallicity, where the metals actually grow in unison with the rate with how you form stars, so you build up your metals over time. And consistently, the blue line shows an exponentially declining star formation history with a free but constant metallicity. And I'm not saying this S-norm function and the evolving metallicity perfectly captures it, because you can see there's a lot of wiggles and features in real star formation histories you can't hope to capture with these simple forms. But I think you'll agree we're doing better at kind of threading the average behavior, certainly in terms of what the metals are doing, okay? Because basically metals ought to grow with time in something that's approximately closed box like a galaxy. So that really motivated, finally, as well as Sabina's stuff, cosmic star formation history making more sense. Claudia's work looking at this really drove home the point that you have to have evolving metals to do sensible things with galaxies. So finally, for every one of our galaxies and GAMA that we fitted and DEVILS, so Jess's later work, we have these star formation kind of histories on the right-hand side, that's in blue, and then we have coupled to that our kind of metallicity growth. So this kind of moves on to more of Jess's stuff, really, because she looked at about 500,000 galaxies in the DEVILS survey, along with 230,000 galaxies in GAMA, to actually look at kind of the star forming main sequence over cosmic time, kind of combining these two surveys and using Prospect to do this inversion. So this is the combined thing. So on the blue side, the left side, you kind of got the DEVILS data, which will always go to lower stellar mass. It's a fainter survey, so the given epoch, the lowest mass things will always be coming from DEVILS, the highest mass things will always be coming from GAMA. And this is kind of evolving over a few windows of metallicity. We go out to about a redshift of, well, the final one is 5 to 9. We pretty quickly start transitioning to having to use photometric redshifts instead of spectroscopic redshifts to do this work. But actually, because of the quality of photometric redshifts we have in DEVILS, so we're not doing that in GAMA, we're just using spectroscopic redshifts. But because of the quality of the multiband data and the kind of mid-width kind of filters you have access to in the DEVILS regions, they're actually relatively high precision kind of redshifts, and they actually turn out to suddenly be good enough to start getting constraints, reasonable constraints on stellar masses and star formation rates. So you can do this inversion out to pretty high redshift. I guess the key bits that came out of that work that Jess did, the first PhD paper, it was really clear kind of the bending you get in the the star forming main sequence, particularly when you combine GAMA with DEVILS. Really, really strong kind of discontinuity in terms of how linear that relation is. But once you get out to high redshift, is actually there's very little evidence, at least in our analysis, for any bending. So a bit on that's kind of the Prospect implementation. The other kind of meaty, or kind of the second very meaty bit we want to get onto is AGN fitting. So all of that early work kind of ignored largely AGN, bar some quite simplistic kind of ways to exclude them from the sample. But really, because the redshifts we're operating at kind of towards cosmic noon, you do need to worry about AGN, and so we worried about doing this properly. Unfortunately, the first way we implemented in Prospect didn't work very well. This was just using a simple template, the simple dust model that tried to approximate the dusty torus and the ISM. That was more or less Jess's master's thesis, which was a very good thesis, but nothing worked. So that wasn't Jess's fault, that was kind of my fault. But when we came back around to doing this during her PhD, we decided to look at a more complicated, kind of physically motivated 3D model, and that started to work really well. So that became the second paper she published. So again, Prospect does have some discussion at AGN, but the really meaty stuff is Jess's paper on the bottom. So looking at volumetric AGN luminosity functions. So again, to look at the little chart, we got various options for AGN templates kind of in the bottom left. One of them, the one we really focus on, is this Fritz template. It's worth saying, well, and Jess did this as an excellent plot, so she put this all together as advertised, but what we're trying to physically represent when we do AGN modeling in kind of speech marks, you can't obviously do the full kind of fully 3D thing, but you have to have in your head the toy model of what's going on. So we clearly have a black hole. We have some accretion disk around it that obviously emits broadband light. There's some sort of dusty torus that obviously when you're looking edge on does a very good job of attenuating that light. We have some borderline kind of cloud regions, largely thought to be inside of the dusty torus regime. Some narrow line regions which are thought to be kind of further away, physically kind of offset from that kind of disk. Mysteriously, physically not exactly known where it's located, but somewhere kind of north and south, probably of your accretion disk, some hot X-ray corona regime. Obviously, in some cases, you've got a synchrotron jet. Put these together, and you kind of have a unification diagram where in the top left, you're looking at radio loud, low electromagnetic power, because you've got quite a faint accretion disk. Top right, you've got your high electromagnetic power, again, with your synchrotron jet. And then bottom right, you got your kind of radio quiet but high power, so you don't have significant radio emission. And bottom left, you got your radio quiet kind of low power AGN. So your four kind of, I'll say four kind of classic ways to divide it, but the reason you can see those little black subregions is things are about to get complicated because Jess was very engaged with a number of people in the AGN community, sent lots of emails, even had like online chats on Zoom to really dig into the details of how these different regions are kind of recognized and named. And it turns out there's almost no complete, interestingly, there's no unification diagram for how people draw unification diagrams. They're not unified. So there's a lot of disagreements even within the community about how best to represent this. But the least offensive way of representing this, I'm sure people who work in AGN, there's always something they're upset by, but roughly they're split into how you might name these different regimes, your angle you're probably looking at your AGN at, and what kind of emissions, so you can see these different colors represent different kind of observations you might be able to make, what you would expect to observe if you're in that class of AGN. And again, it was very interesting and difficult for Jess to get kind of clear answers even from people who work in this field. I think there are people who wanted Seyfert 1.7 galaxies included in the diagram, but by then it was a bit too late. Oh, so taking that diagram, that's kind of our 3D model, keep that in your head. And remember where this starts to be significant, obviously in the X-ray regime, but in the optical, so in the ultraviolet, optical, and infrared and mid-infrared, the contribution of AGN becomes highly non-negligible. So that's where this kind of, well, and eventually if it's radio loud in the radio, so that's where this simplistic kind of sketch starts breaking down. So what happens if you've got no AGN, so the same star formation history, in all cases, we've got this black line on the left, which is then no AGN. We've got a Phaeton galaxy, which is kind of dust-free and has an AGN, and kind of different optical depths of that AGN. So depending on kind of effectively your pseudo viewing angle, the same luminosity AGN can have a very different impact on kind of what your SED ends up looking like. Often does dominate, the most consistent thing is it does dominate in the mid-infrared, I would say. Popular kind of regime using like WISE colors to actually select AGN, but depending on your kind of toy model of how you're viewing it, it can dominate kind of throughout. My toy model, we use the Fritz model, in that wedge, I kind of mentioned Fritz 2009 in the end. You effectively have an observation angle for your kind of unified model, a bolometric luminosity of the AGN, an optical depth for your kind of torus, and a couple of properties, and these are parameters we let be free when we do the fitting, and then optionally in Prospect you could fit these, but we don't because they're too degenerate. You've got things like the ratio of your outer to inner torus ratio, which is telling you something about the depth of the dust you're going through. Different parameters that control the dust, so beta dust and gamma dust in the Fritz model, and the opening angle of the torus. So that will kind of tell you over what regime you start to get attenuated by the light from the torus. So we fix those to like suggested values in the Fritz kind of paper because they just get too degenerate to fit, but we do fit the top three in our kind of pseudo 3D, but not literally 3D, because all these properties are gridded out in the Fritz model. So rather than actually having to fully generate a self-consistent ready-to-transfer model, we can kind of simplify and simulate this. So here's an example of a galaxy that you can start to see decouples away from the AGN-free model in blue on the left. By the time you get to the mid-infrared, we're doing a bad job of representing the data. If we add in this new kind of Fritz-inspired derived AGN model, we get a very consistent fit in mid-infrared. And even you'll notice that UV point on the far left, even that's starting to make a lot more sense once we add in this more complicated kind of 3D motivated AGN model. And the impact that has is pretty huge, particularly on the star history on the right. There's about a factor of 2 difference in the implied star formation history, because a lot of the optical light is being explained by the AGN rather than by star formation. Okay, so this plot is showing what impact adding AGN and those free parameters can have. So we got kind of AGN on and on AGN off on the y-axis in DEX. So things like what impact does it have on the stellar mass as a function of how dominant the AGN is. This is between 5 and 20 microns, which is like the classic way of defining AGN dominance. What fraction of the light in that mid-infrared regime contributes? The cell mass is quite stable, even once you get to a highly AGN dominant kind of regime, even towards 1, your stellar masses are rarely biased by about more than 0.1 dex. But obviously, if you turn the AGN off, you're making things too massive. But the star formation rate, for instance, can be hugely impacted. So once you have a highly dominant AGN, in reality, if you didn't fit for that, then you could be rapidly getting out by 1 or 2 dex for the most powerful AGN. It's not. Hopefully, shouldn't be super surprising. We also, it's a bit more subtle, but there's some impact even on the metallicity and even on the tau. So for this sample, again, we kind of mentioned those numbers earlier. We're fitting about 500,000 DEVILS galaxies, about 230,000 gamma galaxies. We make some selection on kind of our AGN, and this is to make our volumetric AGN luminosity functions. So a safe regime is to say F AGN, this is the fraction of flux contributed between 5 and 20 microns. That's more than 10%, where they start to believe the AGN is robust and use it in this analysis. So we put together a bunch of AGN luminosity functions, volumetric luminosity functions that span redshifts of 0 to about 2. So that's on the right-hand side. Jess's work with GAMA and DEVILS is in blue and purple, so consistent colors with earlier. The selection, kind of where we get incomplete for all sorts of reasons in GAMA and DEVILS is kind of that gray regime. So that tends to be near the peak of our kind of observed luminosity function, volumetric luminosity function. Where it drops off is kind of artificial. But to the right of that, we're looking with a bunch of kind of literature results, which is nice. I mean, we're not pushing, I would say, any aspect of the AGN luminosity function further than other people have before with kind of dedicated studies, but at least it convinced us that our way of modeling AGN was making physical sense, and we're getting back kind of appropriate values kind of cosmically. On the left, you can see how we compare to a bunch of, well, the top's the most interesting simulations, a mixture of semi-analytic models and hydrodynamic simulations. They tend to be a little bit kind of inconsistent with each other, a bit all over the place, particularly as you move to higher redshifts, like that 0.8 to redshift kind of 1 regime. So that's more kind of an open question for that community, how they're going to do better, I guess. So overlap with other techniques. If you have our new AGN luminosities coming out of prospect, an interesting question is how well do they agree with these other ways, these various kind of yellow through to red ways of defining AGN? Classically, they don't always agree that well. One of the first ones to look at was emission line features. So here we looked at a sample from Z Cosmos where we had kind of borderline kind of classed spectra, which were probably AGN. In this case, 53 that were fitted by prospect, 51 do get appreciable FAG1. If you cast that on BPT, so take those same galaxies, look at the BPT diagram, and divided in these classic regimes where we think liners and AGN Seyfert start to dominate. The things which are getting more purple are where our FAGN fraction is going up. So basically, the things which are substantially far away from kind of the liner, the composite and the star forming regime is where we start to get significant evidence of AGN prospect as well. The mid-infrared selection technique, I'd say, isn't as interesting because it's really using the same information we have access to in prospect. You know, mid-infrared colors, prospect uses mid-infrared colors to do its fitting. So not surprisingly, where you see that kind of line drawn recent work asset, where you see that kind of regime of W1 minus W2 versus mag, where they start to select AGN, I'd say not surprisingly, that's also where we start to select AGN. Definitely the least interesting because we're using the same data ultimately. But really neat, I think, is when we started to compare to X-ray data. So on the left is stuff Jess actually had in her paper. So this was as published, comparing to Chandra Cosmos data, looking at implied bolometric luminosities of AGN, the conversion that was made from the X-ray, which is like a classic formula, which I forget off the top of my head, but a way to infer bolometric AGN luminosities from X-ray flux. But even cooler, this isn't published, the right-hand side, looking at E-Rosita, EFEDS data. Again, we got really consistent AGN luminosities, both from prospect using the full kind of UV through to far infrared, as we got from E-Rosita directly using AGN and applying a bolometric correction to the AGN. They're basically completely consistent with a one-to-one line, and the intrinsic scatter, given the errors, is very, very close to zero. That was really, really neat. So I was super happy when that dropped out. So the final cool bit of the puzzle, which I think will give us enough time for some questions, because I didn't want to fill the whole time up with just me talking, is this radio extension part. So that's kind of the main focus in AGN. And now we're going to look at radio extension. So really the only relevant paper as a reference is Jess's most recent one that appeared on arXiv last week. So it's very good timing for this talk. So hopefully some of you noticed that. It's called The Long and the Short of It. We like puns in our titles. The benefits and leverage of ultraviolet to radio galaxy fitting. So that's accepted. I think the temporary version is already on Bunras, so it'll start appearing on ADS probably today or tomorrow. So it's very good timing for this talk. And that was the last paper from Jess's thesis. And she's just kind of fully completed her thesis now. So a lot of this is based on the work of Marvel 2015, and therefore, if you dig down into it, a lot of that is sort of using classic relationships that come from Kennicott in '98 and Murphy in 2011. We basically end up with an equation that defines flux density for your free component, your kind of thermal component of your radio emission. A component that is kind of coupled to that, where you have a controlling factor, which is your fraction free, your free frac, which is 3Fs, which is annoying to say, but that's your synchrotron component. So your non-thermal tends to be associated with other physics, but particularly say supernovae. And obviously put these two things together, and that gives you your kind of radio component. So you basically have two parallel slopes that added together make a sort of bendy, not parallel slope. So that's kind of your right-hand regime here, and you'll see correctly labeled by Luke. Once you get to the millimeter and radio regime, you've got your free regime kind of in burnt red, and on the right-hand side, sort of in pink. All these colors are quite hard to describe verbally, but in the kind of pink, there you've got your synchrotron component from supernovae remnants in particular. Okay, so if we use Prospect in kind of this simple kind of forward generative mode, with like defaults turned on, like literally the classic free frac of 0.1 and a synchrotron power law slope of -0.7, you would get something like this plot. On the right-hand side, you basically have a light blue line, which is where your free fraction starts to dominate the flux, and your green line, which is where the synchrotron component starts to dominate. So obviously some of those ends up being kind of bendy in log space, and as you get towards longer and longer wavelengths, you end up usually being entirely dominated by the synchrotron component. So what we do with this radio extension, and what's kind of interesting, is using see if we can use the 1.4 gigahertz kind of data point to the far right-hand side. Imagine we have a future survey where, thanks to Herschel no longer being operational and not many other survey-grade far-infrared instruments existing, the question is, can we use radio data to constrain effectively our dust emission, and almost can we do as good a job as if we didn't even have the dust measurements in the first place? So that's kind of the question. We tested this on 30 DEVILS galaxies. It's so few because we had to make sure we had very high quality. We already had the UV-FIR high quality data. The really hard bit was getting deep enough, good enough quality, homogeneous, well matched, no kind of catalog kind of matching errors radio data. So we had to throw in an awful lot of the radio data because it just wasn't deep enough or had ambiguous source matches. We also complemented this with 34 galaxies from Kingfisher, where the is like radio extension to the Kingfish survey. So these are nearby NGCs. And these, for the most part, were the 3 data points we had access to: 1.4, 3 gigahertz, 2 gigahertz. So these are all the galaxies that just ended up fitting over quite a large range in dynamical mass. So going from about 8.5 stellar masses all the way to 11.5. They are offset at 10,000 angstrom by 0.5 dex to make it kind of visually kind of understandable. But this is like 3D fitting all the way through to the radio data. So using it in the full fitting mode. Let's get through that. So if we use it in this fitting mode and we fit for the free fraction and we fit for the synchrotron slope, so we free alpha to be -0.1, but we actually allow it to fit the synchrotron alpha, we compare to published values. It's kind of noisy. It's quite hard to constrain these things, but it's kind of consistent within the quality of the data. And this is some examples of the 2 fits. So we could look back at the Tabet 2017 work and compare kind of our summed SEDs, so our kind of black lines compared to those dashed black. They're very consistent given the amount of data, but now we're doing a fully physically consistent fit throughout the whole kind of SED regime, not just the radio data points on their own. If you look at the free frac and the alpha synchrotron as a function of AGN luminosity, then it's quite neat. As you get to very either high F AGN frac or very luminous AGN, you'll see these really radio loud galaxies, which are the things, they do start to drop off this free frac line. So that will be where your free fraction starts to plummet. It's nice because that means you're becoming super synchrotron dominated, which is what we believe should happen if you're already allowed AGN. So that's really nice that that kind of dropped out pretty naturally, gave us some confidence we're doing something that is physically useful. And that final bit, the original reason we did this is the question, well, how bad is it to infer the far infrared if you have no far infrared data, but you just have optical through to near infrared? So that's the black solid data points kind of on the left-hand side. Notice we're even assuming we have no UV data, given that Galaxy isn't operational anymore, and we're assuming we have no mid-infrared and no far-infrared data. So all those empty data points that we have there to see like how well we can reconstruct them, but they're not being used for the fitting. The only difference between the orange and the blue is in the blue case, we also at the far right-hand side make use of the 4.4 gigahertz data point. So using the priors implied by just fitting that huge sample and finding what a reasonable free frac and a reasonable synchrotron, fixing that, and then doing the fit but including all 0.4 gigahertz data point, means you can actually do an excellent job of reconstructing physically meaningful SED, where you're missing quite a huge regime that we'd ideally like to have access to be able to say something meaningful, particularly about glow dust properties. So yeah, like I said, that, but we're using that. Okay, and that brings us to the end. So a few minutes for questions. I didn't want to go on too long, so hopefully I got that about right. But I'm going to put up some plots to simulate some discussion. So reminder, basic SED modeling. The main thing is we have this skewed normal star formation history and this linearly mapped way of building up metals, which we think is super important for getting things like the cosmic star formation history right. We've added AGN, and that do a good job of agreeing with kind of other methods. It's certainly not obviously worse, and gives us a reasonably well constructed AGN luminosity function. And finally, and I think really excitingly, given I work at a radio astronomy institute, is it looks like we can make really good use and meaningful use of continuum radio data, especially big surveys coming up that are going to be missing an awful lot of mid-infrared, far-infrared data that we luckily did have access to in GAMA. So I'm going to leave it there, and thank you very much for your time.
Okay, great. Thanks so much, Aaron. That was a really fantastic talk. That was really, really inspiring, lots of interesting information. So now we open the floor to questions. So I'm going to look at your, please raise your hand. And you can basically, there are not so many people that you can actually just connect your camera and you can speak up. So I think Richard Tufts, yeah, I think you can go ahead, please.
Hey, Aaron, how you doing?
Hello, is that Richard? Hello.
Hi, Aaron. Good to see you again. Thanks very much.
Excellent.
I came in halfway through, but I'm sort of catching up with all your papers. Quick question about the Radio Free.
Yes.
You put up your formula where you link the Radio Free to the far infrared, I think.
Yep. Back here. Yeah. Sorry, let's get to that.
It was one of the last overlays, I think.
Sorry. Yeah.
Yeah. It's just coming up with the
Yeah, that. Sorry, yeah.
Yeah, so that's the formula. Yeah, that's the formula on the left down there.
Yeah.
So I wanted to ask you, you for these galaxies that you've been testing this technique on, you have all UV data. You also have H alpha data, at least for the Kingfish galaxies. And so I wondered if there's another way of predicting the free, which is just to look at the ionizing radiation from the stars, which you must model at some point if you know the star formation history, and then connecting this free flux to that part of the model.
Yeah, so exactly right. So in fact, to do the emission features, that's exactly what we have to physically do. We have a parameter which says, like, where in the Lyman forest do you want to start fully attenuating your flux to then re-emit in your lines. So then you have like an escape fraction parameter. But you do integrate that. So you do then have potentially another route. That is another route to potentially predict what that effectively that FIR term is. So the way we currently get FIR is by integrating our implied far infrared luminosity, which we obviously have in Prospect, but there's possibly a way you can think about it more directly through literally using the ionizing photons that we have access to. I think that would give you a very similar answer, and it's not explicitly how we do it, but that's certainly another thing about coupling them. Off the top of my head, I don't think it would, because of how we do it, and without getting too far into the weeds, I don't think in practice for us that would make a huge difference. It should be pretty consistent. Whenever I've done those checks, they all look pretty consistent. But yeah, you could certainly do that more explicitly, Richard.
Yeah, thanks. All the best, Aaron. Well, I'll get in touch sometime.
Yeah, do email me. Are you still in?
Yeah, no, I'm Heidelberg. Yeah, still plodding on with the radiative transfer.
Cool. No, we should be in touch. Yeah, thanks.
Cheers.
Thanks, Richard. So Any other thought? Any other questions? I mean, I will step in here. So one general thing is that you have this prospect, I mean, this methodology in general, that basically you derive some parameters. So just to give me an idea, because you have so many different bells and whistles, you have the stellar component, you have the dust, you have many other things, the AGN. So how do you incorporate all these parameters into a likelihood? You just put them the way they are? Do you have a special way of statistically dealing with the different parameters that contribute to different parts of the spectrum?
So yeah, when we use it in that, let's say, generative mode, so you want to, and that's literally how Shark, so that semi-analytic model, uses it. You want to put in parameters, like there's 5 parameters that control the star formation history. There's about 4 parameters that control your dust attenuation. There are about 4 parameters that control your dust re-emission. If you have all the bells and whistles on, you potentially have as many as somewhere in the 20s, getting towards 30 parameters. An awful lot of them are unusefully degenerate. So things like eta in the shallow and full model, in practice, everyone who uses that just fixes it because it's too degenerate with how tau behaves without getting too much into the guts of it. So optionally in Prospect, you can have all these things free, but there's so many degeneracies, you have to use some human wisdom of which things are interesting in matter and which things are completely uninterestingly degenerate. And kind of fix them. And for instance, for us, for most of this work, and not to offend anyone here, dust was more of a nuisance parameter than something we wanted to make deep kind of physics of. And sorry, that would probably upset Richard. But that meant we could get away with fixing some of the properties that control dust, knowing that that would mean probably properties like our dust masses wouldn't be as physically meaningful as maybe people in Segal who really wanted to get into the guts of stuff like dust mass. So for us, that's a sacrifice worth making. Simplified the fit-in, meant we had many fewer parameters when we did the fit, so things would converge faster, be less degenerate. But it is something you have to be very aware of using codes like Prospect. If you do or don't care about certain physics, you can get away with starting to treat these things as being nuisance parameters and not worry about the degeneracies. I mean, once you add in all the AGN properties as well and all the radio, actually it ends up being well over 30 parameters, which would then take like hours to converge on a single galaxy fit. Whereas in Jess's case, it was taking more like 10 minutes because she made kind of sensible selections about which parameters were interesting and not degenerate.
Okay, great. Thank you. Ralph, you have a question?
Yeah, I have a question or a comment, Aaron. Thanks first for a very comprehensive talk. My comment is on the first view graph with the circles with these different segments where you described models which you are using, and you separate between dust attenuation and dust emission. So this one, for example, yeah. Of course, beside dimming, absorption of dust, you have scattering, and dust scattering, emission, and absorption. And scattering is, of course, connected by radiative transfer. And the models you're using, Dale and Rain, they ignore this. So would you think that these effects of radiative transfer are completely irrelevant? Or could you give a hint of how much this would impact your results?
Yeah, that's a really fair question. So all of these codes, and I didn't say it explicitly, but what they implicitly have baked into them is the assumption of energy balance, which doesn't quite hold for real galaxies. The fact that if you attenuate light, then the same amount of energy has to be re-emitted. The reason really that starts to break down is as soon as you're in an optically thick regime and you actually have effectively radiation pressure causing and coupling to your dust, causing literally motion in your gas and outflows. Clearly energy balance doesn't make sense because you're not balancing energy. You're coupling some of your radiation to another form of energy, kinetic energy in your gas and dust. And that deep assumption of energy balance just in the electromagnetic spectrum doesn't make sense. So suddenly once you get to high redshift and you've got optically thick dust and potentially outflows driven by AGN winds and starburst winds, then all the assumption all these codes make about energy balance does break down. If you're outside of that regime and you're in effectively an optically thin regime, and you don't have to worry about that EM energy coupling to something other than EM energy, I think in practice you don't need to worry nearly as much. I'd say the biggest flaw of all these approaches, and possibly even radiation transfer codes, but some of this as well, is the fact that you're not really obeying the real universe, especially in the optically thick regime. Indeed, it can't be obeying energy balance. It looks like Richard's got a comment about that.
Yeah. Maybe could I ask a second question? It's also concerning the metallicity which you are wearing. So I do, of course, dust modeling. So if you change the metallicity, you change the abundances, and then you change the cross section of the dust. So I think you're not doing this. So
no. Yeah.
So could you explain a bit better what you do what you change when you change the metallicity?
So the metallicity only changes the metallicity of the gas at the epoch you're forming stars. So our dust, and this is not physically reasonable, but again, other codes are equally physically unreasonable. We don't currently make any attempt to couple our dust properties actually to the metallicity of the gas. I completely agree, that makes more physical sense. And I've often wondered about the best or the least worst way to do that. It's clearly what you'd want to do physically. So it is in my head as an improvement or physically motivated improvement we ought to be making, because currently we treat the dust as if it's completely independent of metallicity in the gas, and it only affects the stars formed, which is a flaw, and it's a flaw I think all of these codes make, and certainly something I would like to improve. So that's a really good insight, and it's something that I've wondered about, but I still haven't got a. With all of this, that one of the issues is obviously you always want to make something more physical, but there's always a practical question at what cost in terms of computation. If you make it too physical, then it becomes intractable to do the kind of studies we've done with kind of millions of galaxies. So that's always at the back of my head, is there effectively a cheap way to approximate that physical coupling between dust, grain size, all the kind of dust properties, and metallicity of the gas. And maybe there is, but I haven't quite figured that out yet, is the honest answer.
Yeah, okay, thanks.
Okay, Richard?
Yeah, thanks. I just wanted to come back on that interesting argument by Aaron about energy conservation and the idea that some fraction of the energy in a photon field might actually be transferred via momentum transfer to kinetic energy. I mean, I believe if you look at the interaction of a grain with a photon field, that in almost all circumstances, except when the radiation can be maintained in an anisotropic form for a very long time, that the kinetic energy transfer actually can be neglected. And it's simply because the speed of the particle is so much smaller than the speed of light. And so I do think that your code is very, very well motivated by the energy conservation. But my only quibble is, Aaron, I think we've personally discussed this in the past several times. That the radiation field, the radiation from galaxies that you see in the optical UV is not isotropic, because these galaxies tend to have disk structures. And pardon me if I'm not fully up to date with Prospect, but my question would be, do you take this into account? The inclination angle. I think I saw inclination angle, which might have been one of your variables, but do you take it into account, and how do you sort of calibrate that without the benefit of a radiative transfer calculation?
So the nearest you get in pure Prospect and the similar codes would be assuming the properties that control your dust attenuation, so tau and eta in the shallow and full model, that effectively they approximate, I'm not saying in detail that's true, but they approximate the effect of changing inclination. So if you looked at the same galaxy edge-on versus face-on and looked at the attenuation curve, that would be captured by a change in tau and a change in eta. What Prospect doesn't do, and none of these codes do, is take those outputs of shallow and full and correct them and convert them into an inclination. But that's almost when I was talking about nuisance parameters, that's effectively what these codes are doing as a nuisance parameter. They don't really understand why the dust might have a different tau and why the dust might have a different eta, but what's potentially captured, and maybe in detail it's not true, and then I agree in detail it won't be, but what they've actually captured is the effect of a change in inclination. I did try to show that in one of the earliest.
Yeah, sorry, I joined a bit late. So
yeah, you probably missed that. But the other code we've worked on, which I didn't discuss here at all, is Profuse, which actually does combine Prospect with a real kind of galaxy model and actually fit the pixel data of galaxies. So it's getting nearer to a radiative transfer kind of approach. I didn't talk about Profuse here because that's like a whole tool itself, but it's basically combining something like Galfit, semi-code Profit, with Prospect to do like a full kind of pixel-based decomposition. But I better leave that there for now. I can talk to you, Richard, more about that offline.
Yeah, let's talk about that offline, Aaron.
Yeah.
It's an interesting question.
Okay, thanks so much. We just have time for a brief question from Omkar.
Yes, thanks. Thanks, Aaron, for the nice talk. I just had a question about the radio SED part again. Do you have plans to add more complex radio SEDs, like effects of free absorption or other kind of energy losses, like inverse quantum, and that can lead to curvatures and other things in the SED?
Yeah, great question. I hinted at, I can show it way back here, this regime. I don't know if you can see my mouse, but
yes,
this is where you're starting to get synchrotron self-absorption. So a couple of things I would like to get, and I don't know anyone, and I know people who work on this, but like a simple physically motivated radio model, but that's currently a bridge too far to do it simplistically. But yeah, the other thing to people here, and particularly over at Curtin, who work on these regimes, like people who work at Gleam and Curtin, ICRAR, actually getting a more physical self-absorption model, because currently we don't have that in there.
I think your voice is breaking, no?
Yeah, the audio was breaking a bit.
Yeah, I think his video is also stuck.
So Aaron, can you hear me? Let me see if I
Oh, hello. Am I back again?
Yeah. The audio was a bit choppy. So
okay, sorry. So yeah, yes, we want to do that, and probably the next obvious thing is to add self-absorption for the continuum and hopefully a physically motivated radio AGN model, but that looks to be very hard to do simplistically, as in it'll probably do more harm than good if you put a very simplistic model in there.
Yeah, thanks. Even for star-forming galaxies, like if you have very compact star-forming regions, there could be free absorption. So even there, for ULERGs, for instance, people sometimes see these effects already. But
we definitely do want to think about adding that in. We've not done that yet, but that's the obvious next step on the radio side. Yeah.